All right, we have made it to week 5, and we are going to continue our study of different fields of mathematics this week in 8.2. Section 8.2 continues modular arithmetic that you were looking at last week. You might have remembered I mentioned this was one of my favorite fields of mathematics. The applications that we're going to look at today. So last week you just did some basic arithmetic using modular arithmetic. This week we're going to look at some actual applications of that arithmetic. And these topics that we're going to look at is actually some of the first mathematics research that I did, dealing with credit cards and check digits and then cryptography. So the first applications that we're going to look at are ISBN numbers and UPC numbers. So ISBN numbers are assigned to books. Every book has a unique number. And then UPC are those product codes that we see in the store. So what's interesting is now those numbers are, they're very easy to deal with because we have computers and scanners and everything is very technological. But when they were developed for use, that was not the case. They've been around for a very long time. And modular arithmetic was used to create what's known as a check digit, so that as clerks or librarians or whoever entered that string of numbers, because ISBN numbers, I think they're 13 digits in length, right? That's a lot of numbers to enter, and it would be very easy to transpose numbers or type a number incorrectly. And then the book is mislabeled or the product is mislabeled and, gets misplaced or can't be found. So what check digits do is the ISBN number has a specific formula. I believe it is done with modular 13 arithmetic, but your book has the formula. You can look because each set of digits has a different modular arithmetic. It adds the digits up through a very specific formula, applies the correct modular arithmetic to it, and if that comes out to be 0, and remember if you're doing modular 13, then 0 is 0, 13 is 0, 26 is 0, right? You have that circular, just like in the clock, every time you hit a multiple of 12, you go back to 12, right? So 12, 24, 36. So if you get one of those numbers, one of those multiples of whatever modular you're using, and you get 0, that indicates that your number was entered correctly. Because if you flip the digits, the formula will not work. So specifically the ISBN number, I think it multiplies different digits by 3, so that when you add it, you'll get a different number. And then if you don't get 0, you know that you entered the numbers incorrectly. So you're going to practice that. You're going to practice applying check digits to different ISBN numbers. UPC numbers use a similar method. You add those numbers up and look for a 0 in the check digit. And if it is there, then most likely you entered the number correctly. Another application, and this is where I did some work in my undergrad degree, is with credit card numbers. So credit card numbers have, they also use check digits. So if you've ever been entering your number into a computer system and it won't take it, right? It says it's incorrect or you didn't enter it right. And you've wondered, how in the world does it know that? That's because every credit card company has its own very specific check digit formula. Also, every credit card company has a very specific prefix. So, for example, Discover card, 6011 is the beginning of every Discover card. So if you say you have a Discover card and you type in something other than 6011, automatically your number has to be incorrect. But in addition to that, in addition to the prefixes having to be correct, the check digit formula also has to be correct. So that means that once you enter your number, the computer can very quickly add up those numbers using the formula that is specific to that credit card company and identify if you entered it correctly or not. So it's just another way to guarantee that human error does not occur when we are typing numbers in. And then the last application that you're going to look at, perhaps a more interesting one, I don't know, is in cryptology. So I also did some of my undergrad research with both credit card check digits and with cryptology. In fact, one of the largest hirers of mathematicians in the country is the NSA and the CIA. And that is because they do a lot of work with cryptography. So, cryptography has to do with encoding and decoding messages. So, if you receive a coded message, is there a way that we can apply mathematical formulas to it to crack it, to see what that code is and read it? For obvious reasons, that's pretty important to governments. And then also, what formula can we apply to encrypt our messages? So here's the message we want to send. What do we need to do to it? How can we encrypt it in a way that it's unbreakable or very difficult to break? I mean, best case scenario, it's unbreakable, right? And so mathematicians do a lot of work with that, not only encrypting messages, but then decrypting. Because if you send an encrypted message, you want the receiver to be able to unencrypt it, to decrypt it, but you want those that shouldn't have access to it to not be able to do that. And so it's a pretty important field that a lot of mathematicians do work in. So you are going to look at what is called a ciphertext, how to switch letters around in a systematic way to encode a message. And you're going to practice that at the end of the lesson. You're going to look at how to rewrite a message with a ciphertext. And then what do you need to unencrypt that ciphertext? So it's kind of a fun lesson, I think, a fun application at the end. And that will kind of wrap up our look at modular arithmetic. So again, this semester we're taking just little glimpses of different fields of mathematics. So that will wrap up modular arithmetic.